Hi, welcome to es346, Introduction to Thermodynamics. This is video 7.9b. The topic is still isentropic efficiency, and the section of the textbook is 7.12. So here are the learning outcomes of this video. At the end of the video, you'll be able to apply the isentropic efficiency equation to a compressor, and you'll know how isentropic efficiency is applicable to a nozzle. So I want to start off reviewing isentropic efficiency, and we'll talk about the turbine first, which we talked about in the last video. So what I show here on the left is called the Moyer diagram. It is a plot of the enthalpy as a function of the entropy. And just for reference, right over here, this is the saturation line. And below that line, I would have mixtures, and above that, I would have vapors. And so we'll look at a turbine that might be operating in the vapor region. And so, for example, we said if we had an inlet pressure of this line over here is 1,000 psia, and if this was not a perfect turbine, maybe it has friction and or turbulence, there would be an increase in entropy. And so as it went down to a lower pressure, and I'm showing a lower pressure right down in here, it's this line right over here, which is 100 psia. It's going to be dropping down to this point, but I have an increase in entropy. Now, if I had no increase in entropy, it could actually go all the way down here. So this is the same low pressure line of 100 psia. We always want to compare the same outlet pressure, so you do an apples to apples comparison between them. All right, now let's go ahead and apply this to a compressor. And so a compressor goes from a low pressure to a high pressure. So here I'm showing coming in at some low pressure, just a few psia. Maybe it's about, I've got about 50 psia here, going up to 100 psia. And if it's not perfect, there's going to be an increase in entropy. It's going to veer to the right. Now the perfect compressor is going to go straight up, and so going to that same high pressure line of 100, it's only going to have a smaller, or an increase in enthalpy up to here, a little smaller amount. So if I look at the energy balance, which says that the work requirement is that change in enthalpy, for the compressor, the perfect compressor actually has a lower input requirement. So remember, the vertical line is the perfect situation. And so now if I wanted to find an efficiency, I'll take the ratio of the perfect amount over the actual amount. So now my efficiency is just sort of reversed from what I had before, where now I've got the minimum work requirement over the actual work requirement. The minimum work requirement means my outlet enthalpy is H2S, which would be the value of a constant entropy. That value will always be less than or equal to 1. And that's one thing to realize if you've got the equation flipped over, is if you're getting efficiencies that are greater than 1. So let's go ahead and apply this to a compressor now, or an example to a compressor. And so I've got a compressor. It's an air compressor. I've got inlet conditions around atmospheric, 100 kPa, 25 C, and I'm told that outlets at 1 megapascal and 350 C, and I want to know what the efficiency is. All right, so here's my efficiency equation. I want to know what the minimum work is. That would be the work that could have been input. It would be less than the actual, so this over here will be my actual work. And again, sticking with the notation of the book, I've got H1 being my inlet enthalpy, and the subscript S meaning the isentropic state. Right? Now, with the air compressors, we're a little different than the examples we did before in that when I've got an ideal gas, remember, if I want to determine what the enthalpy is, well, the enthalpy is only a function of temperature. And in fact, we can say it's simply Cp times T. So if I go ahead and plug that into my efficiency equation, I can go ahead and cancel the Cp terms, and now I've got a simple equation just in terms of temperature to go ahead and find out what my efficiency is. T1 is the inlet temperature, that's given. T2 is the actual temperature, so that would be T sub A, that's given. So the only thing I need to find is T2S, what would be the isentropic temperature. All right, now this is where it deviates a little different from our solution method before, because we're going to use this tool. We're going to use our TDS relation, which tells us how our temperature changes as a function of pressure. That's what I'm using. And this is an isentropic relation, so this value of T2 I'd be calculating here is T2S. I can then go ahead and put that into that upper equation to find the efficiency. So let's go ahead and do that. Go ahead and calculate T2S. I need to use absolute temperatures in this equation because this comes from the ideal gas law. So 298 is at 25 degrees Celsius. Here's my ratio of pressures, and that exponent is K minus 1 over K. And I'm going to use 1.4 as an average value. This comes out to a T2S of 575 Kelvin. So now I can go ahead and apply that back into my efficiency equation. There I've got my T1. This right over here is my T2S. and this value over here is my T2 actual. It's going to be a value somewhat less than 1. It's 0.852, so this would be an 82.5% efficient compressor. So the next topic I want to talk about is how would we apply this to an isentropic to a nozzle to determine an isentropic efficiency of it. So how do you define the efficiency of a nozzle? Well, let's think about what is the point of a nozzle. And a point of a nozzle, well, is essentially to go ahead and make the outlet velocity higher than the inlet velocity. And so from an energy point of view, we think of this as an energy transformation. We're going to be converting enthalpy into kinetic energy. The way I like to think of it is, well, I have a bunch of enthalpy eggs that are going into my nozzle, and then my nozzle is going to go ahead and convert some of that to kinetic energy. So I can go ahead and take one of my enthalpy and turn it into my kinetic energy. And if I had a more efficient nozzle, I'd be able to convert more and more of my enthalpy into kinetic energy. And so there's going to be some maximum amount of kinetic energy I can get, and that would be the isentropic nozzle. So that's how we're going to go ahead and define our efficiency. We're going to define it as our change in kinetic energy of our actual nozzle over the maximum that we could do. All right? So there's the idea between that, and that value will always be less than or equal to 1. Think about what happens if I'm moving eggs from my enthalpy to my kinetic energy basket, right? Enthalpy is going down. That means that the temperature is going to be going down. It's going to be getting colder as the kinetic energy increases as it goes faster and faster at the outlet. All right? So there's kind of the transformation that's going on. Now my energy balance for a nozzle simply says that my change in enthalpy is by change in kinetic energy. So that's just an equation describing the concept we just discussed. So that means I can simply go ahead and use my changes in enthalpy for my changes in kinetic energy. And now I've got an efficiency equation that looks like very similar to what I had before. I've got my efficiency of my actual nozzle over that of an isentropic nozzle. All right. Now, and at this point, when you look at your nozzle, you have to determine whether you're dealing with an ideal gas or not. If you're dealing with an ideal gas, that equation is going to simply become this in terms of temperature, like we saw in our previous example. If it's not an ideal gas, then you're just going to be pulling enthalpy values off of a table. All right, I just want to briefly mention what does that mean to go ahead and have an isentropic nozzle? What does it mean? Well, it turns out it means that there's no change in entropy as I move through. And actually, there's a particular shaped nozzle that will do this. This becomes very important for a supersonic nozzle, a nozzle that where I'm accelerating fluid faster than the speed of sound. And it turns out there's actually a particular shape that actually will accomplish this. And this is discussed in chapter 17 of the book, so it's a little farther than we're going to do. But the idea is that this nozzle is shaped such that it generates no entropy. So there's actually going to be no friction in there, and it's not going to have any turbulence. And the velocity actually increases and increases with no increase in entropy. There's also kind of an interesting thing that once you go faster than the speed of sound, these nozzles actually get larger at the outlet. But that's a topic we won't go into any further here. All right, so let's go ahead and summarize what we talked about in this video. We compared the isentropic efficiency concepts of compressors and turbines, and we calculated an ideal gas compressor efficiency, and then we defined what isentropic efficiency of a nozzle is. All right, that's it. I'll see you next time.